When two particles become entangled, something genuinely strange happens to the fabric of reality as we understand it. Not strange in a mystical sense, but strange in a way that violates our everyday intuitions about how separate objects should behave. Start with a simple scenario. Take a single photon with enough energy and send it through a special crystal called a beta-barium borate crystal. Under the right conditions, that single photon spontaneously splits into two lower energy photons. This process is called spontaneous parametric downconversion, and it's one of the most reliable ways physicists create entangled particles in the laboratory. Here's where things get interesting. Those two photons that emerge don't just fly off as independent particles. They're born connected in a way that has no classical analog. If you measure one photon and find it polarized vertically, the other will be polarized horizontally. If you find one polarized at 45 degrees, the other will be at negative 45 degrees. The correlation is perfect, instantaneous, and holds no matter how far apart the photons travel. The key conceptual shift is this. After the split, you no longer have two separate photons with individual properties. You have one quantum system that happens to occupy two locations in space. The entangled pair is a single entity from the perspective of quantum mechanics. This isn't just philosophical hand-waving, it's encoded in the mathematics. In quantum mechanics, we describe particles using wave functions, which are mathematical objects that contain all the information about a system's possible states. For a single particle, you write down one wave function. For two independent particles, you write down two separate wave functions and multiply them together. But for entangled particles, you can't do this. You cannot write the wave function of the pair as a simple product of two individual wave functions. The mathematical structure simply doesn't factor that way. This irreducibility is the formal definition of entanglement. The particles have lost their individual quantum identities. Think about what this means. Before entanglement, each particle had its own set of properties, its own quantum state, its own wave function. After entanglement, those individual descriptions no longer exist. There's only the joint description. The whole is not just more than the sum of its parts. The parts no longer have independent existence in the quantum sense. Now, you might object. Maybe each particle does have a definite polarization from the moment they split, and we just don't know what it is until we measure it. Maybe there's a hidden instruction encoded in each photon that says, if measured in this direction, show this result. This seems reasonable. It's how we think about classical correlations. If I tear a photograph in half and send one piece to Tokyo and keep the other in New York, there's a perfect correlation. When you look at your half and see the left side of someone's face, I'll see the right side of that same face. But nobody thinks this is mysterious. The information about which half went where was determined at the moment of tearing. The correlation has a simple local explanation. Quantum entanglement is not like this, and we know it's not like this because of a mathematical proof developed by physicist John Bell in 1964, which we'll explore in depth later. But the essence is this. If the particles had predetermined properties, even hidden ones, we could write down predictions for certain measurement combinations. Those predictions set upper limits on how strong the correlations could be. Quantum mechanics predicts correlations that exceed those limits, and experiments confirm the quantum predictions. The correlations are too strong to be explained by any pre-existing local properties. So what's actually happening when we measure one particle and instantly know something about the other? The language we use matters here because it's easy to slip into misleading descriptions. When you measure the first photon and find it vertically polarized, you haven't sent a signal to the second photon telling it to be horizontal. You haven't disturbed it or influenced it through some mysterious action at a distance. What you've done is gain information about the shared quantum state. And because that state is shared, information about one location immediately tells you about the other. Here's an analogy that captures some of this, though like all analogies, it eventually breaks down. Imagine a sealed box containing two coins that were manufactured with a strange property. They must always show opposite faces, but neither has a definite face showing until someone opens the box and looks. The moment you open the box in New York and see heads on your coin, you instantly know the Tokyo coin shows tails. Not because your observation sent a signal to Tokyo, but because the correlation was encoded in the system from the beginning. The quantum version is weirder because the coins genuinely don't have faces showing before you look. This isn't ignorance on our part. The quantum state before measurement is not a state of hidden definite values that we simply haven't accessed yet. It's a state of genuine indefiniteness, a superposition of all possible combinations. The measurement doesn't reveal a pre-existing result. It creates a result from a state that previously had no definite outcome. Let's ground this in actual numbers. Suppose you create an entangled pair of photons in a state that quantum mechanics describes like this. When measured along the vertical-horizontal axis, there's a 50% chance both are vertical and a 50% chance both are horizontal, with a particular phase relationship between these possibilities that makes the state entangled. This is called a Bell state, one of four maximally entangled states that form a complete basis for describing 2-qubit systems. Now measure the first photon. You get vertical. The moment you have this result, the quantum state of the pair undergoes what physicists call wave function collapse. The superposition of both vertical and both horizontal possibilities collapses to just both vertical. The second photon, which a moment ago was in a superposition of vertical and horizontal, is now definitely vertical. This collapse happens instantaneously, even if the second photon is light years away. This is what Einstein called spooky action at a distance, and it troubled him deeply. It seems to violate the principle that no influence can travel faster than light. But there's a subtle resolution to this tension, which we'll examine when we discuss information transmission. For now, focus on the ontological claim. Entanglement means the particles don't have separate quantum states. They share one. State. Measurement of one particle doesn't disturb the other particle. It reveals information about the shared state, and in doing so, updates our description of that state. The entanglement itself is created at the moment the particles interact. In our photon example, it's when the single photon passes through the crystal and splits. In other cases, it might be when two atoms exchange a photon, or when two electrons interact through electromagnetic forces. The key is interaction. Particles that have never interacted, directly or indirectly, cannot be entangled. And here's something crucial that often gets overlooked in popular descriptions. Entanglement is not binary. It's not the case that particles are either fully entangled or not entangled at all. There are degrees of entanglement, quantified by measures like entanglement entropy. Two particles can be partially entangled, meaning their correlation is stronger than classical, but weaker than maximal quantum correlation. There are also different types of entanglement structures. Two particles can be entangled in their polarization, but not in their momentum. Three particles can be entangled in ways that two particles cannot be. These are called genuinely multipartite entangled states, and they have different properties than collections of pairwise entangled particles. The GHZ state, named after Greenberger, Horn, and Zeilinger, is a famous example with three particles. All three are entangled in a way that exhibits quantum correlations between all three simultaneously, not reducible to pairwise correlations. Measuring one particle instantly affects the quantum description of the other two, but in a way that depends on all three together. This becomes important when we think about quantum systems with many particles. In a solid material, you might have billions of entangled atoms. The structure of that entanglement, which particles are entangled with which others, and how strongly, determines many of the material's properties. Superconductivity and superfluidity both involve macroscopic entanglement, where vast numbers of particles share a single quantum state. But we're getting ahead of ourselves. The foundation is this. Entanglement is a specific quantum correlation created by interaction, characterized mathematically by the non-factorizability of the combined wave function, and manifested experimentally through correlations that are stronger than any classical correlation could be. It's not magic. It's not consciousness. It's not a bridge between minds or souls. It's a property of quantum systems that follow precise mathematical laws, make testable predictions, and yield to rigorous experimental investigation. The strangeness is real, but it's the strangeness of nature behaving according to rules different from our everyday intuitions, not the strangeness of the supernatural. When physicists create entangled particles in the lab, they're following recipes, specific wavelengths of light through specific crystals at specific angles, specific laser pulses at specific times applied to trapped ions. The process is repeatable, controllable, and predictable. The outcomes match quantum mechanical predictions to extraordinary precision. The mystery, if there is one, is not in the phenomenon itself, but in what it implies about the nature of reality. Entanglement forces us to reconsider what we mean by separate objects and local properties. It suggests that the universe at its foundation is not made of independent building blocks, but of relationships and correlations that transcend spatial separation. That's the real conceptual revolution. Not spooky telepathy, but a fundamental interconnectedness built into the mathematical structure of quantum theory. And that interconnectedness, as we'll see, has been confirmed by decades of increasingly sophisticated experiments that close loophole after loophole, leaving less and less room for alternative explanations. To understand why entanglement seems so impossible, you need to understand what quantum mechanics says about particles before you measure them. This isn't just a gap in our knowledge. It's a fundamental feature of how nature works at small scales. In classical physics, a particle always has definite properties. A ball has a definite position and a definite velocity at every moment, whether you're looking at it or not. Your measurement simply reveals these pre-existing values. You might not know where the ball is until you look, but the ball itself knows exactly where it is. Quantum mechanics rejects this picture entirely. A quantum particle doesn't have a definite position until you measure it. It exists in what's called a superposition of multiple possible positions simultaneously. And this isn't a statement about our ignorance. The particle genuinely doesn't have a single location. It's smeared out across space in a way that has real, measurable consequences. The wave function is the mathematical object that encodes this superposition. For a single particle, the wave function is a complex valued function defined over all possible positions. At each point in space, the wave function has a value. The square of the absolute value of that number gives you the probability of finding the particle at that location if you measure it. Here's the crucial bit. Before measurement, the particle isn't secretly at one of these locations, with us just being ignorant of which one. The particle is described completely by the wave function, which assigns amplitude to every possibility simultaneously. The particle is, in a real sense, in all these places at once, though with different amplitudes. You can demonstrate this through interference experiments. Send a single electron through a double-slit apparatus. If the electron went through one slit or the other as a definite particle with a definite path, you'd see two bright spots on the detector screen behind the slits. But you don't. You see an interference pattern with bright and dark fringes. This pattern emerges because the electron's wave function passes through both slits, and the two parts of the wave function interfere with each other, constructively in some places, destructively in others. The interference pattern is direct evidence that the electron was not in a definite location as it passed through the slits. It was in a superposition of passing through the left slit and passing through the right slit. Both paths contributed to the final outcome. This works even if you send electrons one at a time, so it's not a matter of electrons bumping into each other. Each individual electron interferes with itself. Now extend this to other properties. A photon can be in a superposition of vertical and horizontal polarization. Not vertically polarized, not horizontally polarized, but both at once, with specific amplitudes for each possibility. A spin 1/2 particle, like an electron, can be in a superposition of spin up and spin down along any axis you choose. An atom can be in a superposition of its ground state and an excited state, simultaneously absorbing and not absorbing a photon. The mathematics is precise. For a two-level system, the quantum state is written as a combination of the two basis states. You might write it as state equals alpha times state 0 plus beta times state 1, where alpha and beta are complex numbers whose squared magnitudes sum to 1. Alpha squared gives the probability of measuring the system in state 0. Beta squared gives the probability of finding it in state 1. Before measurement, the system is in this superposition. It's not in state 0 with some probability and state 1 with some other probability in the way a classical system might be in one state or another, but we don't know which. The superposition is a fundamentally different kind of state. It has properties that neither pure state 0 nor pure state 1 has on its own. For instance, you can measure the system in a different basis, a different set of states. Depending on the values of alpha and beta, the system might be in a definite state in this new basis, even though it's in a superposition in the original basis. This is impossible for a classical probability distribution. A classical system that's definitely in some state in one description must be in a probabilistic mix in other descriptions. Quantum superpositions don't work this way. The phase relationship between alpha and beta matters. Change the phase, the angle of these complex numbers in the complex plane, and you don't change the probabilities of measuring state 0 or state 1, but you do change the probabilities of measurements in other bases. This phase information is physically real. It's what creates interference patterns. Now comes the measurement problem, which is both a technical issue and a deep conceptual puzzle. When you measure a quantum system in a superposition, you get a definite result. Measure the electron's position, and you find it at a specific location. Measure the photon's polarization, and you find it either vertical or horizontal, not some weird combination. The superposition collapses. The wave function, which was spread out over many possibilities, suddenly concentrates on the single outcome you observed. After you measure the electron and find it at position X, the wave function becomes sharply peaked at position X. The probability of finding it there on an immediate subsequent measurement is nearly 100%. The other possibilities vanish. This collapse is discontinuous and instantaneous. It's completely different from the smooth, deterministic evolution the wave function undergoes when the system is not being measured. Between measurements, The wave function evolves according to the Schrödinger equation, which is a differential equation that changes the wave function gradually and predictably over time. But the moment a measurement happens, this equation stops applying, and the wave function jumps discontinuously to a new state. Quantum mechanics gives you precise rules for calculating the probabilities of different measurement outcomes, but it doesn't tell you which outcome you'll get in any particular instance. It's fundamentally probabilistic. Einstein hated this. He believed a complete physical theory should predict definite outcomes, leading him to his famous remark that God does not play dice with the universe. But every test of quantum mechanics has confirmed the probabilistic predictions. Here's where things get genuinely weird. What counts as a measurement? When exactly does the collapse happen? If you measure a particle's position using a detector, and the detector clicks, the particle's wave function has collapsed. But the detector is also a physical system made of quantum particles. Shouldn't it be in a superposition of clicked and not clicked until someone looks at it? And if you look at the detector, aren't you also a physical system made of quantum particles? This is the measurement problem in its sharpest form. Quantum mechanics doesn't give you a clear dividing line between the quantum system being measured and the classical measuring apparatus. In principle, everything is quantum. But in practice, we seem to observe definite measurement outcomes, not superpositions of outcomes. One response is to say that measurement is special, that the act of observation by a conscious observer causes the wave function to collapse. This was seriously proposed by some of the founders of quantum mechanics, and it still has adherents today. But most physicists find this unsatisfying. It seems to give consciousness a privileged role in physics without any clear mechanism for how consciousness would cause collapse. Another response is the many worlds interpretation, which says there is no collapse. The wave function always evolves smoothly according to the Schrödinger equation. When you measure a particle in a superposition, you yourself enter a superposition. One branch where you observed outcome A, another branch where you observed outcome B. Both outcomes happen in different branches of the wave function. You just can't see the other branches. We'll return to this later. For now, the operational description is this. Quantum systems exist in superpositions until measured. Measurement yields a definite result with probabilities given by the squared amplitudes in the wave function. After measurement, the system is in a definite state corresponding to the measurement outcome. This applies to entangled systems in a particularly striking way. When two particles are entangled, their joint wave function is in a superposition of correlated states. For our earlier photon example, the state might be photon A vertical and photon B vertical, plus photon A horizontal and photon B horizontal. Both pairs of outcomes are present in the superposition simultaneously. When you measure photon A and find it vertical, the joint wave function collapses. The photon A horizontal and photon B horizontal part of the superposition vanishes instantly. Only the photon A vertical and photon B vertical part remains. Photon B, which was in a superposition of vertical and horizontal, is now definitely vertical. This is the mechanism behind the instantaneous correlation. It's not that measuring photon A sends a signal to photon B. It's that measuring photon A collapses the shared wave function, which describes both photons together. Since that wave function is shared, collapsing it affects the description of both particles simultaneously, regardless of the spatial separation between them. But here's the subtlety. This doesn't allow you to send information faster than light. If you measure photon A, you get a random result, vertical or horizontal with 50-50 odds. The person measuring photon B also gets a random result, perfectly correlated with yours, but still random from their perspective. Neither of you can control what result you get. You can't encode a message in your measurement outcome because you can't choose your measurement outcome. The correlation only becomes apparent when you compare your results later, through classical communication that travels at or below the speed of light. Until you talk to each other, neither of you knows you're seeing correlated outcomes. The instantaneous collapse doesn't give you instantaneous communication. This resolution preserves relativity while accepting the reality of instantaneous wave function collapse. It's an uneasy piece, and different interpretations of quantum mechanics handle it in different ways. But the mathematical predictions are clear and experimentally verified. The superposition principle is what makes quantum computers potentially powerful. A quantum computer with 300 qubits can be in a superposition of 2 to the 300th power states simultaneously, more states than there are atoms in the observable universe. Quantum algorithms exploit this massive parallelism, performing operations on all these states at once. But when you measure the result, you get only one outcome. So the trick is designing algorithms that amplify the amplitude of the correct answer while canceling out wrong answers through interference. Superposition is fragile. Interact with the environment, collide with air molecules, absorb a stray photon, couple to vibrations in the surrounding material, and the superposition degrades. The system transitions from a pure quantum superposition to a classical mixture of possibilities, where it actually is in one state or another, but we don't know which. This process, called decoherence, is why we don't see everyday objects in superpositions. We'll explore it in detail later, but for now, understand that maintaining superposition requires exquisite isolation from the environment. The strange thing about quantum superposition is that it's simultaneously the most experimentally verified aspect of quantum mechanics and the most conceptually troubling. We can create superpositions reliably, manipulate them precisely, and extract interference effects that confirm their existence. But we still don't have consensus on what they mean, whether the electron really is in multiple places at once, or whether we're just using convenient mathematical tools that happen to make accurate predictions without corresponding to underlying reality. What we do know is that treating superposition as real, as a genuine feature of quantum systems, rather than merely a reflection of our ignorance, allows us to make predictions that match experiments to absurd precision. And when you combine superposition with entanglement, you get correlations that simply cannot be reproduced by any theory in which particles have definite properties all along. That's what makes the combination so powerful and so strange. Superposition means particles don't have definite properties. Entanglement means particles that have interacted don't even have individual wave functions. Put them together, and you get a picture of reality that's deeply non-intuitive, but experimentally unassailable. In 1935, Einstein, along with collaborators Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics must be incomplete. The argument became known as the EPR paradox, and it set up a challenge that would take nearly 3 decades to resolve mathematically, and another decade beyond that to test experimentally. Einstein's intuition was that quantum mechanics worked perfectly well as a calculational tool, but it couldn't be the final word on physical reality. Something deeper had to be going on. Perhaps there were hidden variables, properties of particles that quantum mechanics didn't track but that determined measurement outcomes in advance. If such variables existed, then particles would have definite properties all along, and the apparent randomness of quantum measurements would just reflect our ignorance of these hidden details. This wasn't mere philosophical preference. Einstein had a specific principle in mind: locality. the idea that an event at one location cannot instantly affect an event at a distant location. This principle is baked into special relativity. Information and causal influence cannot travel faster than light. If measuring a particle here instantly determines the state of a particle light years away, as quantum mechanics seemed to suggest, then either information is traveling faster than light, or the distant particle already had a definite state before the measurement. Einstein favored the second option. He thought, entangled particles must carry hidden information from the moment they're created. Information that determines what result each particle will give when measured. The perfect correlations arise not from spooky action at a distance, but from pre-coordination at the source. For almost 30 years, this seemed like a reasonable position. Quantum mechanics made its predictions, and theories with hidden variables could potentially reproduce those predictions while satisfying locality. There was no obvious way to decide between them experimentally. Then, in 1964, a physicist named John Bell proved something remarkable. He showed that any theory satisfying Einstein's assumptions, any theory where particles have definite properties determined by local hidden variables, must make predictions that differ from quantum mechanics in certain experimental situations. He derived an inequality that all local hidden variable theories must satisfy, and he showed that quantum mechanics violates this inequality. Bell's theorem is mathematical, but the underlying logic is accessible. Start with Einstein's assumptions. Assume particles have hidden properties assigned when they're created. Assume measuring one particle cannot affect the other if they're far apart. Now consider an experiment where you measure both particles along different axes, different angles for polarization measurements. For any specific hidden variable configuration, each particle will give a definite result when measured along any particular axis. The results might depend on the hidden variable, but they're determined in advance. The correlation between the two particles' results depends on what hidden variables they share. Now, here's the key. If you measure particle A along axis 1 and particle B along axis 2, you get some correlation. If you measure A along axis 1 and B along axis 3, you get another correlation. If you measure A along axis 2 and B along axis 3, you get a third correlation. Bell showed that for any local hidden variable theory, these three correlations must satisfy a particular inequality. They can't all be too large simultaneously. The specific form is usually written as the absolute value of the correlation for axes 1 and 2, plus the absolute value of the correlation for axes 1 and 3 must be greater than or equal to the correlation for axes 2 and 3 minus 1. This is one version of what's called the CH-SH inequality, named after Clauser, Horn, Shimoni, and Holt, who reformulated Bell's original inequality into a more experimentally accessible form. Quantum mechanics violates this inequality. For certain choices of measurement angles, quantum mechanics predicts correlations that are too strong to be explained by any local hidden variable theory. The quantum correlations exceed what any prearranged agreement between the particles could produce while respecting locality. The violation isn't subtle. For the optimal choice of angles, the CH-SH inequality says the combined correlations can't exceed 2. Quantum mechanics predicts a value of 2.828, 2 times the square root of 2. Experiments consistently measure values close to the quantum prediction, clearly violating the inequality. This is not a loophole or a technicality. It's a rigorous mathematical proof that certain experimental results are impossible for any local hidden variable theory to reproduce. And nature produces exactly those impossible results. Let's make this concrete with polarization measurements on entangled photons. Suppose you create a pair in the state we discussed earlier, both vertical or both horizontal in equal superposition. Now measure photon A at angle 0 degrees and photon B at angle 45 degrees. Quantum mechanics predicts they'll match about 85% of the time. Measure A at 0 degrees and B at 90 degrees, and they'll match about 50% of the time, completely uncorrelated. Measure A at 45 degrees and B at 90 degrees, and again about 85% matching. Now try to explain this with hidden variables. Maybe each photon carries instructions. If measured at 0 degrees, say vertical. If measured at 45 degrees, say vertical. If measured at 90 degrees, say horizontal. You can work through all possible instruction sets and calculate what correlations they produce across different measurement combinations. No matter how you assign the instructions, you can't reproduce the quantum predictions. The quantum correlations are too perfect when the angles are close and too weak when they're orthogonal. Hidden variables can get close in some cases, but they can't match the quantum predictions across all angle combinations simultaneously while respecting locality. Bell's theorem tells you something profound. Nature is either non-local or doesn't have definite properties before measurement, or both. You can't have particles with pre-existing definite values and locality. Something has to give. The experiments to test this started in the early 1970s with work by Stuart Friedman and Clauser, then continued with increasingly sophisticated tests through the decades. Alain Aspect's experiments in the early 1980s were particularly influential. He created entangled photon pairs, sent them to distant detectors, and measured polarizations at different angles. The results violated Bell's inequality, matching quantum predictions. But early experiments had loopholes, possible alternative explanations that could save local realism. The detection loophole arose because photon detectors in those days were inefficient, catching only a small fraction of photons. Maybe the detected photons weren't representative of all photons, and a clever hidden variable theory could exploit this selection bias. The locality loophole was even more subtle. If the choice of what angle to measure isn't made until after the particles are created, but before they reach the detectors, and if that choice is made independently at each detector, then there's no time for information about one measurement choice to reach the other particle before it gets measured. This ensures that the correlations can't arise from any signal traveling between the detectors. Closing both loopholes simultaneously required extraordinary experimental sophistication. Fast random number generators to choose measurement angles at the last possible moment. High-efficiency detectors that catch nearly every photon. Large enough separation between detectors that light couldn't travel from one to the other in the time between measurement choice and detection. Precise timing to verify that the measurements were space-like separated, outside each other's light cones. In 2015, 3 independent experiments finally closed all major loopholes simultaneously. Groups in Delft, Vienna, and Boulder each performed definitive tests. They created entangled particles, made measurement choices at the last moment using fast random number generators or quantum processes, detected the particles with high efficiency, and verified that the measurement events were space-like separated. All 3 experiments violated Bell's inequality, confirming the quantum predictions. The Delft experiment used entangled electrons in diamond nitrogen vacancy centers separated by more than a kilometer. The Vienna experiment used entangled photons separated by 60 meters, but with detection efficiencies above 75%, high enough to close the detection loophole. The Boulder experiment used entangled photons with detection efficiencies above 75% and verified space-like separation. These experiments won the 2022 Nobel Prize in Physics for Aspect, Clauser, and Anton Zeilinger. The Nobel Committee's statement was clear. These experiments demonstrated the violation of Bell inequalities and pioneered quantum information science. What do these results mean? They mean local hidden variables don't exist. Particles don't carry predetermined instructions about how to respond to measurements. The correlations are genuine quantum correlations, not arising from shared classical information. But Bell's theorem doesn't tell you how to interpret this. It doesn't favor one interpretation of quantum mechanics over another. Copenhagen, many worlds, pilot wave theory, and other interpretations all predict the same violation of Bell inequalities because they all reproduce standard quantum mechanics predictions for these experiments. What Bell's theorem rules out is a particular kind of common-sense realism, the idea that particles have definite properties independent of measurement, and that influences can't travel faster than light. You can keep locality if you give up definite properties. You can keep definite properties if you give up locality, but you can't keep both. Most physicists favor giving up definite properties. This fits naturally with the Copenhagen interpretation and its descendants. The wave function collapse is non-local, but no information is transmitted, so relativity is preserved where it matters, in preventing faster-than-light signaling. Some interpretations, like pilot wave theory, keep definite properties and accept non-locality. In this view, particles do have definite positions at all times, guided by a non-local wave that coordinates their behavior. The non-locality is explicit and unavoidable, but again, it can't be used to send signals faster than light. What you can't do anymore, after Bell, is maintain the comfortable classical picture where distant objects are truly independent and have definite properties. The universe doesn't work that way. Bell's theorem, combined with its experimental verification, is one of the most important results in 20th century physics, precisely because it rules out what seems like the most intuitive model of reality. Einstein was wrong, but he was wrong in an interesting way. He identified the key issue, the apparent non-locality of quantum mechanics, and he articulated clearly what assumptions would be needed to avoid it. Bell showed those assumptions can't all be true simultaneously, and experiments confirmed Bell's analysis. The EPR paradox, meant to show quantum mechanics was incomplete, instead revealed something deep about the structure of reality. Nature violates Bell inequalities. That's an experimental fact. How you interpret that fact, what picture of reality you construct to accommodate it, remains a matter of interpretation. But the fact itself is not in dispute. The correlations are real, stronger than classical, and exactly as quantum mechanics predicts. The most persistent myth about quantum entanglement is that it allows faster-than-light communication. Science fiction loves this idea. Entangled particles as cosmic telephones, letting you send messages across the galaxy instantaneously. It's a compelling notion, and the intuition behind it seems reasonable. If measuring one particle instantly affects its entangled partner, why can't you use that to transmit information? The answer is precise and unforgiving. Because you can't control what result you get when you measure your particle, and neither can the person on the other end. Both of you see random outcomes. The correlation only becomes visible when you compare your results later through normal communication channels that obey the speed of light limit. Let's work through exactly why this is. Suppose you have one member of an entangled pair and your friend has the other, now separated by a light year. You want to send a message, maybe a simple bit, a 0 or a 1. You measure your particle. You get some result, say spin up. Your friend measures their particle and gets spin down, perfectly correlated with your result. But here's the problem. You getting spin up and them getting spin down doesn't encode any information from you to them. From their perspective, they measured their particle and got spin down. That's consistent with you having measured and gotten spin up, but it's equally consistent with you not having measured at all. The particle gives them spin down with 50% probability whether you measure or not. You might think, what if I measure along a different axis? What if my choice of measurement axis changes what they see? It does change their results in a statistical sense, but it doesn't change any individual outcome in a way they can detect without comparing notes with you. Here's why. Before you measure, your particle is in a superposition, and so is theirs. If you measure along the vertical axis and get spin up, their particle is now definitely spin down along that axis. If you had measured along the horizontal axis and gotten spin up there, their particle would now be definitely spin down along the horizontal axis. Your choice of measurement axis determines what state their particle ends up in. But when they measure their particle, they don't know what state it's in. They don't know what axis you measured along. They just point their detector in some direction and see what they get. If they happen to measure along the same axis you did, they'll get the opposite result every time. If they measure along a different axis, they'll get probabilistic results that depend on the angle between the axes. Crucially, they can't tell from their measurement results alone whether you measured or not, or what axis you measured along. Their results look random either way. The only way they can see the correlation is to compare their list of results with your list of results, and that comparison requires classical communication. Let's make this concrete with numbers. Suppose you're trying to send a bit by choosing between two measurement strategies. To send a 0, you measure along the vertical axis. To send a 1, you measure along the horizontal axis. Your friend always measures along an axis 45 degrees between vertical and horizontal. If you send a 0 by measuring vertical, you get spin up or spin down with equal probability. Let's say you get spin up. Your friend measures at 45 degrees and has equal probability of getting spin up or spin down along their axis due to the angle between measurement directions. The correlation exists, but their individual result is still random. If you send a 1 by measuring horizontal, again you get a random result, and your friend gets a random result at 45 degrees. The correlations in the two cases are different. The statistics of matching versus non-matching are different, depending on whether your axes are aligned or perpendicular. But any single measurement your friend makes gives them a random result regardless of what you chose. They'd need to perform many measurements to gather enough statistics to determine what axis you measured along. But you've only got one particle. You can only do one measurement. They can only do one measurement. There's no way to extract enough statistics from a single pair to determine what measurement you performed. You might wonder about more elaborate schemes. What if you had many entangled pairs? Couldn't you measure each one, creating a pattern in their results? The answer is still no. Each pair gives uncorrelated random results from their perspective. You measuring your half of each pair doesn't create any detectable pattern in their measurement results until they compare with you. There's a theorem that formalizes this impossibility, the no communication theorem. It states that for any entangled state and any choice of measurements on one particle, the statistics of measurement outcomes on the other particle are independent of what measurement was performed on the first particle. The local statistics don't change, only the joint statistics. What you see when you compare results show the correlation. The proof is straightforward. In quantum mechanics, the probability of getting a particular result when measuring particle B is calculated by taking the quantum state, applying the measurement operator for particle B, and tracing out the degrees of freedom of particle A. This mathematical operation of tracing out, summing over all possible states of particle A, has the property that it doesn't matter what measurement you did or didn't do on particle A. The result is the same. This isn't a limitation of current technology. It's not something you could overcome with better detectors or cleverer protocols. It's a fundamental feature of quantum mechanics. The structure of the theory guarantees that. Entanglement can't be used for faster-than-light communication. The same reasoning applies to more exotic proposals. Maybe you could use entanglement for quantum teleportation. This is a real phenomenon in quantum information science, but it's misnamed. Quantum teleportation does let you transfer a quantum state from one location to another using entanglement, but it requires sending classical information about measurement results through normal channels. The classical information is essential. Without it, the person receiving the teleported state has only a particle in a seemingly random state. What about using entanglement to synchronize clocks or coordinate events? Again, the correlation is useless until you compare results classically. If you're trying to coordinate when to take some action, each person sees only their random measurement results. They can't tell from those results when the other person measured. They'd need to send signals back and forth to coordinate, and those signals obey the speed of light limit. Could you use quantum entanglement to give yourself an advantage in special relativistic scenarios? Maybe to maintain simultaneity across different reference frames? No. The correlations exist in a frame-independent way, but detecting those correlations still requires classical comparison of results. Different observers might disagree about the order in which measurements happened, but they'll all agree on the correlations once results are compared. This has implications for causality. Even though entanglement seems to involve instantaneous influence, it can't create causal paradoxes. You can't use entanglement to send information back in time or to affect events in your own past. The structure of the theory prevents this automatically. There's a related misconception about quantum entanglement and consciousness or telepathy. The idea that entangled particles are somehow connected gets metaphorically extended to suggest that human minds might be entangled, allowing psychic connections between people. This is completely unsupported by physics. First, as we've established, even if your brain states were entangled with someone else's, which they aren't for any practical or theoretical reason, this wouldn't allow you to communicate. You'd just see random neural firing patterns, uncorrelated from your perspective with anything the other person was experiencing. Second, entanglement is incredibly fragile. It requires exquisite isolation from the environment. Your brain is a hot, wet, noisy biological system in constant interaction with its environment. Any quantum coherence that might exist at the molecular level decoheres essentially instantaneously, on timescales of femtoseconds to picoseconds for most biologically relevant processes. There's no mechanism for maintaining the kind of coherent, entangled states needed for quantum effects to be relevant to brain function at the cognitive level. Third, there's no evidence from neuroscience or psychology that supports quantum effects playing a role in cognition, let alone entanglement between brains. The brain operates through chemical and electrical signals that are well understood classically. Appeals to quantum mechanics in explaining consciousness are generally made in the absence of any specific mechanism or evidence, filling gaps in our understanding with quantum mysticism rather than addressing the actual hard problems of consciousness. Entanglement doesn't allow telepathy, doesn't connect souls, doesn't enable astral projection or remote viewing. It's a correlation between quantum systems that obey specific mathematical laws and can't be used to violate causality or send information faster than light. The same applies to proposed quantum effects in biology more generally. There are genuine quantum effects in photosynthesis, where quantum coherence plays a role in energy transfer efficiency. There's quantum tunneling in enzyme reactions. Some species of birds might use quantum effects in magnetoreception for navigation. These are interesting and legitimate areas of research, but they're specific, well-defined quantum mechanical processes, not mysterious quantum consciousness or entanglement at the scale of organisms. When people invoke quantum mechanics to explain paranormal phenomena, they're almost always misunderstanding or misrepresenting what quantum mechanics actually says. Quantum mechanics is strange, but it's strange in specific, mathematically precise ways. It doesn't give you a license to believe anything you want about spooky connections or mystical forces. The real physics is plenty strange without embellishment. Entanglement gives you correlations that can't be explained by any classical mechanism. It forces you to reconsider basic assumptions about locality and reality. It enables new technologies like quantum cryptography and quantum computing. These are genuine revolutions in our understanding of nature and what's physically possible. But it doesn't break causality. It doesn't allow faster-than-light communication. It doesn't connect consciousness across space and time. The limitations are as fundamental as the phenomenon itself. Entanglement is a precisely defined quantum correlation with precisely defined properties and precisely defined limitations. Respecting those limitations is part of respecting what the physics actually tells us about the universe. Quantum entanglement is fragile in a way that has no classical analog. The correlations that seem so robust in laboratory settings, perfect anti-correlations, violations of Bell inequalities, the whole strange apparatus of quantum mechanics, all of this disappears remarkably quickly when the quantum system interacts with its environment. This process is called decoherence, and it's the primary reason we don't see quantum superpositions and entanglement in everyday life. It's not that quantum mechanics stops applying at large scales. It's that large objects are never isolated. They're constantly interacting with air molecules, photons, vibrations, electromagnetic fields, and countless other environmental degrees of freedom. Each interaction leaks information about the quantum state into the environment, and this destroys the coherence needed for quantum effects. Think about what it takes to keep a quantum state intact. You need the system to evolve according to the Schrödinger equation without any measurement-like interactions. But measurement isn't some special process involving conscious observers or lab equipment. Measurement, in the relevant sense, is any interaction that correlates the system's state with something in the environment in an irreversible way. When a photon from your quantum system scatters off into the environment, it carries information about the system's state. If the system was in a superposition of state A and state B, and a photon scatters differently depending on which state the system is in, then after scattering, the photon is entangled with the system. The system plus photon is now in a superposition of photon goes left and system in A, plus photon goes right and system in B. This is still a pure quantum state, still coherent in principle. But the photon is gone, flying off into the environment where you have no hope of tracking it. From the perspective of the system alone, tracing over the photon's state, the system looks like it's in a classical mixture, partially in state A, partially in state B, with no definite phase relationship between them. The superposition has effectively collapsed into a classical probability distribution. This is decoherence. It's not that the quantum information is destroyed, it's that it becomes inaccessibly spread out across the environment. The environment acts as a measurement device, continuously monitoring the system and recording information about it in a way that can't be recovered. The timescale for decoherence depends on how strongly the system couples to the environment and how many environmental degrees of freedom are involved. For a single photon traveling through optical fiber, decoherence can be slow, microseconds or even milliseconds if the fiber is good. For a dust particle in air, decoherence happens in femtoseconds. For a human-sized object, decoherence would be essentially instantaneous on any timescale we can measure. Let's get quantitative. The decoherence time is roughly inversely proportional to the rate at which the environment gains information about the system. Each scattering event, each photon absorbed or emitted, each interaction with a nearby molecule contributes to decoherence. The total decoherence rate is the sum of contributions from all these processes. For a spatial superposition, an object being in two places at once, the decoherence rate increases with the separation between the two positions. If you have a particle in a superposition of being at position X and position Y, photons scattering off it will scatter differently depending on where it is. The further apart X and Y are, the bigger the difference in scattering, the more rapidly information leaks into the environment. This means larger superpositions decohere faster. A molecule in a superposition of two positions 1 nanometer apart might maintain coherence for microseconds in a good vacuum. The same molecule in a superposition with positions 1 millimeter apart would decohere almost instantly, even in the best vacuum you can create, because the difference in how it scatters photons is so much larger. Entanglement is even more fragile. When you have two entangled particles, each one is interacting with its local environment. If either particle decoheres, the entanglement is destroyed. You effectively have two independent sources of decoherence. So the entanglement survives only as long as both particles remain coherent. For photons, this means entanglement can survive as long as the photons are traveling through clean optical fiber or empty space. But any absorption, scattering, or loss of one photon destroys the entanglement of the pair. For atoms or ions, entanglement can be maintained as long as they're well isolated, trapped in ultra-high vacuum with minimal stray light and vibration. But bring them into contact with room temperature air, and the entanglement vanishes in nanoseconds. Temperature is a major factor. Thermal photons, blackbody radiation from warm objects, constantly bombard any system at finite temperature. Each thermal photon that interacts with your quantum system can cause decoherence. The rate increases with temperature because there are more thermal photons at higher temperatures, and they have higher energies. This is why quantum computing experiments often operate at millikelvin temperatures, cooled by dilution refrigerators to just a few thousandths of a degree above absolute zero. At these temperatures, thermal photon rates are low enough that qubits can maintain coherence for milliseconds or even seconds, long enough to perform quantum computations. At room temperature, most qubit designs would decohere in microseconds or faster. But there are exceptions. Some quantum systems are naturally resistant to certain types of decoherence. Topological qubits, still largely theoretical, would encode information in global properties of the system that are robust against local perturbations. Certain nuclear spins in molecules can maintain coherence for seconds, even at room temperature, because they couple very weakly to electromagnetic fields and thus to most environmental noise. Decoherence is what makes quantum computing difficult. You need to perform operations on qubits faster than they decohere, or you need quantum error correction, using multiple physical qubits to encode one logical qubit in a way that protects against decoherence. Current quantum computers operate just barely in the regime where this is possible. They can perform hundreds or thousands of operations before decoherence destroys the quantum state. For quantum communication, decoherence limits how far you can send quantum information. Photons traveling through optical fiber are gradually absorbed and scattered. After a certain distance, tens to hundreds of kilometers depending on the quality of the fiber, you've lost most of your photons, and the remaining entanglement is too weak to be useful. This is why quantum communication networks use quantum repeaters, devices that extend the range by creating entanglement in shorter segments and then linking those segments together. Decoherence also explains why you can't just scale up quantum systems to arbitrary sizes and expect quantum effects to persist. The argument sometimes made in popular science that because quantum mechanics is fundamental, everything is really quantum, and we just don't notice it, are technically true but misleading. Yes, everything is quantum. But for macroscopic objects, decoherence is so fast that quantum effects are completely washed out on any observable timescale. There's been interesting work on pushing the boundaries of this. Researchers have created superpositions of larger and larger objects. Molecules with hundreds of atoms have been put into superpositions of different positions and shown to produce interference patterns. Superconducting circuits with billions of atoms have been put into superpositions of different current states. But these experiments require extraordinary isolation and operate for only brief moments before decoherence sets in. The largest superpositions to date involve objects with masses around 10,000 atomic mass units, large molecules, separated by nanometers and maintained for microseconds. This is impressive, but still far from everyday scales. There's no prospect of putting a cat or a person or even a bacterium into a meaningful quantum superposition. The decoherence would be too fast. This has implications for interpretations of quantum mechanics. Some people worry about the Schrödinger's cat thought experiment, where a cat in a sealed box is supposedly in a superposition of alive and dead. Decoherence resolves this in a practical sense. The cat is a macroscopic object in constant interaction with its environment. It decoheres essentially immediately. There's no meaningful period during which the cat is in a superposition. Different interpretations handle the details differently. In the Copenhagen interpretation, decoherence explains why we observe definite outcomes. The environment acts as a continuous measurement, collapsing the wave function. In many worlds, decoherence explains why different branches become independent. The entanglement with the environment makes it impossible for branches to interfere with each other. In either case, decoherence explains why macroscopic objects behave classically. There's a subtlety here worth noting. Decoherence doesn't solve the measurement problem in a fundamental sense. It doesn't tell you why we see one outcome rather than another, or why the wave function appears to collapse at all. What it does is explain why we don't see superpositions of macroscopically distinct states, why the quantum world appears classical at large scales. The deeper questions about the nature of measurement and observation remain interpretation dependent. For practical purposes, decoherence is the enemy. It's what you're fighting against when you try to build quantum technologies. Every improvement in quantum computer performance is ultimately about reducing decoherence rates or speeding up operations to beat decoherence. Every advance in quantum communication is about maintaining entanglement, despite decoherence from transmission losses and environmental noise. But decoherence is also unavoidable. It's a direct consequence of quantum mechanics applied to systems that interact with their environment. You can minimize it by careful engineering, better vacuum, lower temperatures, clever encoding schemes, but you can't eliminate it unless you can perfectly isolate your system, which is impossible. The timescales involved are worth internalizing. For photons in fiber, coherence times of milliseconds. For superconducting qubits, coherence times of tens to hundreds of microseconds. For trapped ions, coherence times up to seconds. For nuclear spins, coherence times up to minutes or hours. For macroscopic objects, coherence times far below a nanosecond. These aren't arbitrary numbers. They come from fundamental physics, how strongly the system couples to photons, phonons, and other environmental excitations, and how many such excitations are present at the operating temperature. Improving these numbers is possible, but hard, requiring advances in materials, fabrication, and control techniques. The bottom line is that entanglement doesn't persist on its own. It requires active protection. The perfect correlations that violate Bell inequalities exist only for as long as both particles remain coherent. Once decoherence sets in, the entanglement degrades into classical correlations, then into no correlation at all, as information about the system is lost to the environment. This fragility is both a challenge and a feature. It's a challenge for quantum technologies, but it's also what allows the classical world to emerge from quantum mechanics. Without decoherence, everything would remain quantum, and the macroscopic world would be a strange superposition with no definite outcomes. Decoherence gives us the appearance of collapse, the emergence of classicality, and the stable macroscopic world we need inhabit. Creating entangled particles in a laboratory isn't magic, but it does require precision. The methods vary depending on what kind of particles you're working with and what you need them for, but all of them share a common principle. You need particles to interact in a way that leaves them in a shared quantum state. The most common method for creating entangled photons uses a process called spontaneous parametric down conversion. Take a nonlinear crystal, beta barium borate is the standard choice, and shine a laser through it. Most photons pass straight through unchanged. But occasionally, a high-energy photon interacts with the crystal's atomic structure and splits into two lower-energy photons. Energy conservation requires that the energies of the two daughter photons sum to the energy of the parent photon. Momentum conservation requires that their momenta sum to the parent photon's momentum. These conservation laws create correlations between the two photons. They emerge from the crystal in a shared quantum state, entangled in their polarization, their momentum, or both, depending on the crystal orientation and the type of down conversion process. There are two types of spontaneous parametric down conversion, type 1 and type 2. In type 1, both daughter photons have the same polarization, perpendicular to the parent photon's polarization. In type 2, the two daughter photons have orthogonal polarizations. Type 2 is particularly useful for creating entanglement in polarization because you can arrange things so the photons emerge in a superposition of both horizontally polarized and both vertically polarized. The efficiency is low. Only about 1 in a billion photons undergoes down conversion in typical setups. You need a bright laser and good detectors to catch the rare entangled pairs. But the process is reliable and well understood. You can predict the properties of the output, photons from the crystal parameters, and the input laser wavelength. Once you have the photon pairs, you need to verify they're actually entangled. This means measuring correlations. You send one photon to detector A and the other to detector B, with polarizers in front of each detector. By rotating the polarizers to different angles and recording which combinations of detector clicks occur together, you can reconstruct the correlation function and check whether it violates Bell inequalities. Coincidence detection is crucial here. You're not just counting individual detector clicks, you're counting coincidences, cases where both detectors click within a narrow time window, indicating they detected photons from the same entangled pair. This requires precise timing electronics that can register events to within nanoseconds or better. For trapped ions, the method is completely different. You start with ions held in electromagnetic traps, usually radio frequency traps that use oscillating fields to confine charged particles in vacuum. Laser cooling brings the ions down to near their quantum mechanical ground state of motion. Then you use precisely tuned laser pulses to manipulate their internal quantum states. An ion has electronic energy levels, different configurations of its electrons around the nucleus. You can use lasers to excite the ion from the ground state to an excited state. By carefully choosing the laser frequency and intensity, you can put the ion into a superposition of ground and excited states. This gives you a qubit. To entangle two ions, you use their shared motion. The ions in a trap interact through the electromagnetic field of the trap itself, which couples their positions. A laser pulse can be tuned to simultaneously affect an ion's internal state and its motion. By applying the right sequence of pulses, you can create a state where the ion's internal states are correlated through their coupling to the shared vibrational mode of the trap. The resulting state might look like this. If ion 1 is in its ground state, ion 2 is in its excited state. And if ion 1 is in its excited state, ion 2 is in its ground state, with both possibilities in superposition. This is a maximally entangled state, analogous to the Bell states for photons. Trapped ion systems offer some of the highest fidelity entanglement available. You can create entangled states with better than 99% fidelity and maintain them for seconds or longer. The drawback is complexity. Each ion requires individual addressing with laser beams, precise control of trap parameters, and exquisite isolation from environmental noise. Superconducting circuits offer another approach, particularly relevant for quantum computing. A superconducting qubit is a macroscopic circuit, millimeters in size, that behaves quantum mechanically because it's made of superconducting materials cooled to millikelvin temperatures. The qubit states correspond to different current flows or different charge configurations in the circuit. To entangle two superconducting qubits, you couple them through a shared circuit element, a capacitor or inductor that allows them to interact electromagnetically. By applying microwave pulses at specific frequencies, you can drive transitions that create entanglement. The standard 2-qubit gate for superconducting qubits is the controlled NOT gate, which flips the state of one qubit depending on the state of another. Running this gate with qubits initially in superposition produces entangled states. The advantage of superconducting qubits is scalability. You can fabricate many qubits on a single chip using microfabrication techniques adapted from the semiconductor industry. Current quantum computers from companies like IBM and Google use superconducting qubits arranged in two-dimensional lattices with controllable coupling between neighbors. The disadvantage is coherence time. Superconducting qubits decohere relatively quickly, tens to hundreds of microseconds, because they're large, coupling to many electromagnetic modes in their environment. Researchers are constantly working on better designs, better materials, and better shielding to extend coherence times. For detecting entanglement, you need to measure the correlations between the particles. With photons, this means polarization measurements. With ions, you measure their internal states by shining light that causes ground state ions to fluoresce, while excited state ions remain dark. With superconducting qubits, you use microwave pulses to read out the qubit state by monitoring how the qubit affects a resonant circuit. The key measurement for verifying entanglement is the correlation function. For 2 qubits, you measure both qubits in various bases and calculate how often you get correlated results. If the qubits are entangled, the correlation function will show patterns that can't be explained classically. Specifically, you can test for violation of Bell inequalities or other entanglement witnesses, mathematical criteria that distinguish entangled states from separable states. There are subtleties in the measurements. Photon detection is probabilistic. You lose many photons to losses in the optical system and detector inefficiency. You compensate by repeating the experiment thousands or millions of times to gather statistics. Ion state detection is high fidelity. You can correctly identify the state more than 99% of the time, but still requires careful calibration. Superconducting qubit readout introduces noise and has imperfect fidelity, typically 90 to 99% depending on the design. Another experimental challenge is state tomography, fully characterizing the quantum state you've created. For 2 qubits, the state is described by a density matrix, which has 16 real parameters. To measure all of these, you need to perform measurements in multiple bases and reconstruct the density matrix from the statistics. This is computationally intensive and becomes exponentially more difficult as the number of qubits increases. For special states like maximally entangled Bell states, you can verify entanglement without full tomography. Measuring in just a few bases and checking for violation of Bell inequalities is sufficient. This is what's done in the loophole-free Bell tests we discussed earlier. Recent experiments have pushed entanglement to larger systems. Groups have entangled thousands of atoms in Bose-Einstein condensates, though the entanglement structure in these systems is more complex than simple pairwise entanglement. Researchers have entangled photons, not just in polarization, but in high-dimensional spaces using orbital angular momentum, creating qubit entanglement, where particles can be in superpositions of many states rather than just 2. There have also been experiments entangling different types of particles. Photons entangled with phonons, quantized vibrations in a solid. Superconducting qubits entangled with microwave photons in cavities. Trapped ions entangled with photons emitted during state transitions. These hybrid systems are important for quantum networks, where you might want to store quantum information in long-lived matter qubits, but transmit it using photons. Distance records for entanglement distribution keep extending. Entangled photons have been sent through optical fiber over hundreds of kilometers. Using satellites, entangled photons have been distributed between ground stations thousands of kilometers apart. China's Mischius satellite, launched in 2016, has demonstrated entanglement distribution over 1,200 kilometers, far beyond what's possible with fiber due to losses. The satellite approach works because photons traveling through the vacuum of space experience much less loss than photons in fiber. The main challenges are atmospheric, turbulence when the photons enter or exit the atmosphere, and the need for precise pointing to ensure the photons from the satellite reach the ground detectors. Despite these challenges, satellite-based quantum communication is becoming practical. For quantum computing applications, the goal isn't just creating entangled pairs, but creating and maintaining entangled states of many qubits. Current quantum computers can reliably entangle dozens of qubits. Google's Sycamore processor has 53 qubits. IBM's latest processors have over 100 qubits. These systems can create complex entangled states involving all the qubits, though maintaining coherence across all qubits simultaneously is challenging. The experimental techniques are diverse, but they all come down to controlled interactions that correlate quantum states, followed by measurements that verify the correlations exceed classical bounds. The field has matured from proof-of-principle demonstrations to engineered systems that reliably produce entanglement on demand. This transition from basic science to quantum engineering is what's enabling the quantum technologies we'll discuss next. Quantum cryptography is the first practical application of entanglement that's moved beyond laboratories and into actual deployment. The fundamental idea is simple. Use quantum mechanics to detect eavesdropping. Any attempt to intercept quantum information necessarily disturbs it in a way that reveals the presence of the eavesdropper. The most widely implemented protocol is called BB84, named after Charles Bennett and Gilles Brassard, who proposed it in 1984. It doesn't actually require entanglement. It uses individual photons in various polarization states. But the security comes from the same quantum principles. Here's how it works. Alice wants to send Bob a secret key, a string of random bits that they can later use to encrypt messages. She prepares photons in one of 4 polarization states: vertical, horizontal, diagonal at 45 degrees, or diagonal at -45 degrees. Vertical and horizontal represent bit values 0 and 1 in what's called the rectilinear basis. The 2 diagonal polarizations represent 0 and 1 in the diagonal basis. Alice randomly chooses which basis to use for each photon and randomly chooses which bit value to encode. She sends the photons to Bob. Bob doesn't know which basis Alice used for each photon, so he randomly chooses a basis to measure each arriving photon. About half the time, he'll happen to choose the same basis Alice used. When that happens, he gets the correct bit value. The other half of the time, he chooses the wrong basis, and his measurement result is random. After all the photons are sent, Alice and Bob communicate over a public channel. Alice doesn't reveal the bit values, but she does reveal which basis she used for each photon. Bob reveals which basis he used. They keep only the bits where their bases matched and discard the rest. This leaves them with a shared string of random bits that forms their secret key. Now, consider what happens if an eavesdropper, Eve, tries to intercept the photons. She has the same problem Bob has. She doesn't know which basis Alice used for each photon. If Eve measures a photon in the wrong basis, she gets a random result, and worse, she disturbs the photon's polarization state. When she forwards the photon to Bob, it's no longer in the state Alice prepared. It's in whatever state Eve's measurement collapsed it to. This introduces errors in Bob's measurements. Even when Bob measures in the correct basis, he might get the wrong result because Eve's measurement already disturbed the photon. Alice and Bob can detect this by comparing a random sample of their key bits over the public channel. If they see more errors than would be expected from normal transmission noise, they know someone is eavesdropping, and they abort the key exchange. The security here is provable, not just computational. It doesn't rely on the difficulty of factoring large numbers or any other mathematical hard problem that might be solvable with better algorithms or more powerful computers. It relies on the laws of quantum mechanics, which state that measuring a quantum system in an unknown state necessarily disturbs it. An eavesdropper can't gain information without leaving detectable traces. Entanglement-based protocols like E91, proposed by Arthur Eckert in 1991, offer even stronger security guarantees. Instead of Alice sending quantum states to Bob, a source in between them sends entangled photon pairs, one photon to Alice and one to Bob. Alice and Bob each measure their photons in randomly chosen bases. When they compare results, they can calculate correlation functions and test for violation of Bell inequalities. If the inequalities are violated, they know they have genuine quantum entanglement, which means the photons weren't measured or tampered with in transit. They can then use their measurement results to generate a shared secret key. The beauty of E91 is that the security is verified by the Bell inequality violation. If an eavesdropper intercepts and measures the photons, Even if they try to generate new entangled pairs to send on to Alice and Bob, the correlations will be weakened. The Bell inequality violation will be reduced or eliminated. Alice and Bob will detect this and abort. Real-world implementations face practical challenges. Photons get lost in transmission. Detectors sometimes produce false clicks. Environmental noise introduces errors. All of these effects reduce the rate at which you can generate secure key bits and potentially create vulnerabilities that a clever eavesdropper might exploit. The detection loophole from Bell tests reappears here. If detectors are inefficient and an eavesdropper can selectively block photons to exploit this, security might be compromised. Modern quantum key distribution systems use high-efficiency detectors and careful statistical analysis to close this loophole. The distance limit is another challenge. Photons traveling through optical fiber are gradually absorbed. After about 100 kilometers through standard telecom fiber, you've lost most of your photons. Direct transmission beyond this distance becomes impractical because the key generation rate drops to near zero. Quantum repeaters can extend the distance by creating entanglement in segments and linking the segments together through entanglement swapping. This is a process where you have two entangled pairs, A, B, and C, D. By performing a joint measurement on particles B and C, you can entangle particles A and D, which never directly interacted. This lets you build long-distance entanglement from shorter segments. Quantum repeaters are still largely experimental. They require quantum memories to store photons while waiting for successful entanglement swaps, and they require high-fidelity operations to avoid accumulating errors. Commercial quantum key distribution systems currently operate either over relatively short distances using fiber or over longer distances using satellites. Several quantum communication networks are now operational. The Beijing-Shanghai Quantum Network spans over 2,000 kilometers using trusted nodes, intermediate stations that receive and resend quantum states without full quantum repeater capability. It's used for secure communication between banks and government facilities. Europe has the SECO-QC network connecting multiple cities. Japan has the Tokyo QKD network. South Korea is building a nationwide quantum communication infrastructure. These are early-stage deployments, with limitations in key generation rate and distance, but they demonstrate that quantum cryptography has moved from laboratory curiosity to practical technology. The security guarantees need careful statement. Quantum key distribution provides information theoretic security for the key distribution process itself, assuming your devices work as intended and haven't been tampered with. But if Eve has access to Alice's or Bob's equipment, she can bypass the quantum channel entirely. Device-independent QKD protocols, which verify security based only on observed correlations without trusting the measurement devices, are an active research area but not yet practical. Also, quantum key distribution only solves the key distribution problem. You still need classical encryption to actually encrypt your messages using the shared key. If your classical encryption is weak, or your endpoint security is compromised, quantum key distribution doesn't help. It's one layer in a complete security system, not a magic bullet. The threat model matters. Quantum key distribution is particularly relevant given the development of quantum computers, which would break current public key cryptography schemes like RSA. With a large-scale quantum computer, you could factor the large numbers that secure current internet communications, breaking the encryption. Post-quantum cryptography, classical encryption algorithms believed to be secure against quantum computers, is being developed and standardized. NIST recently selected several post-quantum algorithms for standardization. These will likely be the primary solution for most applications, being easier to deploy than quantum key distribution. But quantum key distribution offers something post-quantum cryptography can't: provable security based on physical law rather than unproven mathematical assumptions about problem hardness. For high-security applications where you need confidence that your communications will remain secure decades into the future against any conceivable computational advances, quantum key distribution is attractive despite its higher cost and complexity. The key generation rates are still relatively low. Current systems might generate secure key bits at rates of kilobits to megabits per second over short distances, dropping to much lower rates at longer distances. This is sufficient for sharing encryption keys, which are relatively short, but not for encrypting streaming video or high-bandwidth data directly. You use the quantum channel to establish keys, then use those keys with classical encryption for actual data transmission. There's ongoing work on improving every aspect of quantum key distribution. Better photon sources that generate single photons on demand rather than relying on weak laser pulses. Better detectors with higher efficiency and lower dark count rates. Better protocols that are more robust to noise and losses. Better integration with existing fiber optic networks. One promising direction is chip-scale integration. Current quantum key distribution systems use bulk optics, separate lasers, crystals, lenses, detectors on optical benches. Researchers are working to integrate these components onto photonic chips, which would make systems smaller, more stable, and cheaper to manufacture. Another direction is moving more functionality into satellites. Ground-based fiber networks are limited by absorption losses. Satellite-based systems can distribute entangled photons globally, creating worldwide quantum communication networks. China's Michias satellite demonstrated this capability, and other countries are developing their own quantum communication satellites. The economics are still challenging. A quantum key distribution system costs tens to hundreds of thousands of dollars, compared to essentially free key exchange using classical public key cryptography. The cost is justified only for applications where security is critical enough to warrant the investment. As technology matures and scales, cost should decrease, but quantum key distribution is unlikely to replace classical cryptography for everyday applications. What quantum cryptography demonstrates is that quantum mechanics isn't just a source of fundamental puzzles. It's a resource that enables capabilities impossible with classical physics. The same entanglement that troubled Einstein now provides practical security for communication networks. This transition from foundational questions to engineering applications is characteristic of quantum information science more broadly. Quantum computing relies on entanglement as a fundamental computational resource. Without entanglement, a quantum computer would offer no advantage over a classical computer. With it, quantum computers can potentially solve certain problems exponentially faster than any known classical algorithm. The basic unit of quantum information is the qubit. Unlike a classical bit that's either 0 or 1, a qubit can be in a superposition of 0 and 1 simultaneously. A single qubit in superposition isn't particularly powerful. You could simulate it easily on a classical computer. The power comes from having multiple qubits entangled with each other. Consider 3 classical bits. At any moment, they're in one of 8 possible states: 000, 001, 010, and so on through 111. You can manipulate these bits, flipping them according to logic gates, but you're always working with one definite state at a time. Now consider 3 qubits. They can be in a superposition of all 8 possible states simultaneously. When you apply quantum gates, operations that manipulate the qubit states, you're effectively performing operations on all 8 possibilities at once. This is quantum parallelism. But there's a catch. When you measure the qubits at the end of the computation, you get only one of the 8 possible outcomes, chosen probabilistically according to the amplitudes in the superposition. You can't directly read out the results of computations on all 8 states. You get one answer, and it's random unless you've carefully arranged the computation so the correct answer has high probability. This is where entanglement becomes crucial. By entangling qubits, you create correlations between them that can't be reproduced classically. These correlations let you design quantum algorithms where wrong answers interfere destructively. Their amplitudes cancel out, while correct answers interfere constructively, concentrating probability on the right result. The canonical example is Shor's algorithm for factoring large numbers. Given a large number n, factoring it into prime factors is believed to be hard classically. No known algorithm can do it efficiently for numbers with thousands of digits. But Shor's algorithm can factor n in time that grows only polynomially with the number of digits, which is exponentially faster than the best-known classical algorithms. The algorithm works by transforming the factoring problem into a period-finding problem, then using quantum Fourier transform to find the period. The quantum Fourier transform operates on a superposition of many possible periods simultaneously, using entanglement to create interference patterns that concentrate probability on the correct period. Measure the result, extract the period, and use it to find the factors classically. Shor's algorithm is a major reason for interest in quantum computing. RSA encryption, used widely on the Internet, relies on the difficulty of factoring large numbers. A quantum computer running Shor's algorithm could break RSA, compromising huge amounts of encrypted data. This threat is why post-quantum cryptography is being urgently developed. Another famous quantum algorithm is Grover's search algorithm. Given an unsorted database of n items, finding a specific item requires checking about n items classically. You have to look through them one by one. Grover's algorithm can find the item in roughly the square root of n steps by using quantum superposition to search multiple entries in parallel and quantum interference to amplify the amplitude of the correct entry. The speedup is quadratic, not exponential like Shor's algorithm, but it's still significant for large databases. More importantly, Grover's algorithm is provably optimal for unstructured search. No quantum algorithm can do better, which tells us something fundamental about the limits of quantum computational speedup. These algorithms require entanglement to work. You need many qubits in correlated superpositions, with carefully designed operations that preserve and manipulate the entanglement structure. When decoherence destroys entanglement, the quantum algorithm fails, and you're left with classical random noise. Measuring the amount of entanglement in a quantum computation is technically complex, but there are quantitative measures. Entanglement entropy quantifies how much entanglement there is between one subset of qubits and the rest of the system. For many quantum algorithms, the entanglement entropy grows during the computation, peaks somewhere in the middle, then decreases as the algorithm concentrates probability on the answer. This growth of entanglement is what makes quantum computations hard to simulate classically. When qubits are unentangled, you can simulate the system efficiently by tracking each qubit separately. When they're maximally entangled, the quantum state requires exponential classical resources to represent because you need to track correlations between all possible combinations of qubit states. There's a distinction worth making between quantum advantage and quantum supremacy. Quantum advantage means using a quantum computer to solve a practical problem faster than classical computers can. Quantum supremacy, now sometimes called quantum computational supremacy, to avoid the problematic connotations of supremacy, means performing any task, even a contrived one with no practical application, that's demonstrably beyond classical computational capability. Google claimed to achieve quantum supremacy in 2019 with their Sycamore processor. a 53-qubit superconducting quantum computer. They performed a specific sampling task, generating random numbers with particular statistical properties that they estimated would take 10,000 years on the best classical supercomputer. Their quantum computer completed it in 200 seconds. IBM disputed the claim, arguing that with optimized algorithms, a classical computer could perform the same task in days rather than millennia, which wouldn't constitute a convincing demonstration of supremacy. The debate highlights how slippery the definition of supremacy is. As classical algorithms improve, the bar keeps moving. More recently, in 2023, IBM and others have demonstrated quantum computations with over a 4,100 qubits. These systems are approaching the regime where they might solve practically useful problems that classical computers can't efficiently handle. But we're not there yet. Current quantum computers are noisy, intermediate-scale quantum devices, NISQ devices, that can perform impressive demonstrations but aren't yet practical for most applications. The noise comes from decoherence and imperfect gate operations. Every quantum gate introduces some error. After enough gates, errors accumulate and destroy the quantum computation. Current systems can perform hundreds to thousands of gates before errors dominate. For many interesting algorithms, you'd need millions or billions of gates, which requires quantum error correction. Quantum error correction encodes each logical qubit in many physical qubits, using redundancy to detect and correct errors. The theory is well developed. There are proven quantum error correcting codes that can suppress errors arbitrarily if the physical error rate is below a threshold. But implementing error correction requires overhead. You might need 1,000 physical qubits to encode one error-corrected logical qubit. Current quantum computers don't have enough qubits or low enough error rates to implement full error correction. They operate in the NISQ regime, where you try to design algorithms that complete before errors accumulate too much. This limits what problems you can solve, but it's still interesting for near-term applications. Potential applications include quantum simulation, using a quantum computer to simulate other quantum systems like molecules or materials. Classical computers struggle to simulate quantum systems with many particles because of the exponential growth in computational complexity. A quantum computer, being itself a quantum system, can potentially simulate other quantum systems efficiently. This has applications in drug discovery, where understanding molecular interactions requires quantum mechanical calculations. In materials science, where designing new materials with specific properties requires understanding quantum mechanical behavior of electrons in solids. In chemistry, where reaction dynamics involve quantum effects that are hard to simulate classically. Quantum machine learning is another area of exploration. Some machine learning algorithms can potentially be sped up on quantum computers, though the details are still being worked out. It's not clear yet which machine learning tasks will show quantum advantage and how large that advantage will be. Optimization is another target application. Many practical problems involve finding the best solution from among many possibilities. Routing delivery trucks, scheduling flights, designing supply chains. Some of these problems can be mapped onto quantum computing architectures in ways that might offer speed-ups, though again, the practical advantages are still being evaluated. The key point is that quantum computers aren't universally faster than classical computers. They're faster for specific problems that have structure, allowing quantum interference to concentrate probability on correct answers. For many everyday tasks, browsing the web, editing documents, playing videos, quantum computers offer no advantage. The entanglement structure in quantum algorithms is often complex. It's not just pairwise entanglement between neighboring qubits, it's multipartite entanglement involving many qubits simultaneously in intricate patterns. Understanding and characterizing this entanglement is an active research area because it helps identify which problems might benefit from quantum computing and how to design better algorithms. There are also proposals for quantum computing architectures that go beyond the standard gate-based model. Topological quantum computing would use anyons, exotic quasiparticles in certain materials, whose braiding creates quantum gates that are inherently resistant to certain types of errors. Adiabatic quantum computing would encode problems in energy landscapes and use quantum tunneling to find low-energy solutions. These approaches require different types of entanglement and might be better suited for different problem classes. The field is moving rapidly. Qubit counts are increasing, error rates are decreasing. New algorithms are being developed. But we're still in the early stages. The quantum computers we have today are comparable to the room-sized vacuum tube computers of the 1940s. Impressive demonstrations of new principles, but not yet practical for most purposes. Whether quantum computing will transform computation the way classical digital computers did, or whether it will remain a specialized tool for specific problems, is still unclear. What's certain is that entanglement is the resource that makes quantum computing possible at all. Without entanglement, quantum computers would be no more powerful than classical computers with random number generators. Entanglement is what gives quantum computing its distinctive power and its distinctive challenges. The mathematics of quantum mechanics makes predictions, and experiments confirm those predictions with remarkable precision. But the mathematics doesn't tell you what's really happening. It doesn't tell you what the wave function is, whether particles have properties before measurement, or why measurement seems to collapse superpositions into definite outcomes. These questions belong to the interpretation of quantum mechanics. An interpretation is a story you tell about what quantum mechanics means, what's really going on beneath the mathematical formalism. Different interpretations make the same experimental predictions because they're all implementations of the same underlying mathematics. They differ in their claims about reality, causation, and the role of measurement. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, is historically dominant, though less so today. It says the wave function is not a description of physical reality, but a tool for calculating probabilities of measurement outcomes. Quantum systems don't have definite properties until measured. Measurement causes the wave function to collapse, yielding a definite result. What happens between measurements is not described by the theory and perhaps not meaningful to ask about. Copenhagen avoids many conceptual problems by drawing a hard line between the quantum system and the classical measuring apparatus. The quantum system is described by the wave function. The classical apparatus isn't. Measurement is a special process that bridges these two domains. This division is pragmatic, but conceptually troubling because in principle, everything is made of quantum particles. There's no fundamental line between quantum and classical. The Copenhagen interpretation also tends to emphasize the role of the observer. Some versions suggest that conscious observation causes collapse, though this was never a universal position among Copenhagen adherents and is not taken seriously by most contemporary physicists. The more common Copenhagen view is that measurement, defined operationally as an irreversible interaction with a macroscopic apparatus, causes collapse, with consciousness playing no special role. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. It says the wave function is real and always evolves according to the Schrödinger equation. There is no collapse. When you measure a quantum system in a superposition, you yourself enter a superposition. One branch where you observed outcome A, another where you observed outcome B. Both outcomes happen in different branches of the universal wave function. Each branch contains a version of you who observed a definite result. The branches don't interact with each other due to decoherence, which makes them effectively independent universes. From within any branch, it appears that only one outcome occurred, but the global wave function contains all outcomes. Many worlds solves the measurement problem by denying that it exists. Measurement is just ordinary quantum evolution applied to systems large enough to decohere. There's no special collapse process. Everything is deterministic at the level of the universal wave function. The wave function evolves smoothly according to known laws. The apparent randomness arises because you experience only one branch, and you can't predict which branch you'll find yourself in. The cost of many worlds is ontological extravagance. The interpretation commits you to the existence of an enormous, possibly infinite, number of branches containing all possible measurement outcomes of all quantum processes throughout the history of the universe. Most physicists find this troubling, though many worlds has gained adherents in recent decades, particularly among quantum information theorists. There's also a technical problem with making sense of probability in many worlds. If all outcomes happen, why do some outcomes seem more probable than others? Various proposals have been made, counting branches in different ways, using decision theory to define rational betting behavior, invoking the Born rule as a normative principle rather than a predictive one. None are universally accepted, and this remains an active area of philosophical debate. Pilot wave theory, also called de Broglie-Bohm theory or Bohmian mechanics, takes yet another approach. Particles always have definite positions, guided by a wave that evolves according to the Schrödinger equation. The wave is real. It's a physical field that fills space, and it influences particle trajectories. Particles surf on this wave, their velocities determined by the wave's structure at their locations. In pilot wave theory, measurement doesn't collapse anything. The wave function continues to evolve. What happens is that particle positions become correlated with detector states in a way that looks like collapse from a practical standpoint. But fundamentally, particles were always somewhere definite, following deterministic trajectories. The theory is explicitly non-local. The wave guiding one particle can depend instantaneously on the positions of distant particles if they're entangled. This non-locality is used to reproduce the violations of Bell inequalities. Particles don't have hidden local variables determining their measurement outcomes. They have definite positions, and their behavior is governed by a non-local guiding wave. Pilot wave theory is attractive because it provides a clear ontology. Particles exist, have positions, follow trajectories. And it's deterministic if you know both the wave function and the particle positions. Cost is that it's explicitly non-local and seems to require a preferred reference frame, which sits uneasily with relativity. Extending pilot wave theory to relativistic quantum field theory has proven difficult. There's also the question of what status the wave function has. Is it physically real, or is it just a mathematical device for calculating how particles move? If it's real, you have two parallel ontologies, particles and waves, which seems redundant. If it's not real, you need to explain why the Schrödinger equation governs a non-real mathematical object, and why this non-real object appears in the guiding equation for particles. The relational interpretation, developed by Carlo Rovelli, takes a more radical view. It says quantum states are not absolute but relative to observers. The state of a system is defined only with respect to another system that could potentially measure it. Different observers can assign different states to the same system, and both assignments are correct relative to their respective perspectives. In this view, there's no global wave function of the universe. There are only states of subsystems relative to other subsystems. Measurement is an interaction that establishes correlations between systems. What looks like wave function collapse is just the establishment of these correlations. The apparent paradoxes of quantum mechanics arise from incorrectly assuming states are absolute rather than relational. The relational interpretation dissolves the measurement problem by denying that there's a universal fact about whether a measurement has occurred or what outcome resulted. From the perspective of the measured system plus apparatus, a definite outcome occurred. From the perspective of an external observer who hasn't yet interacted with the apparatus, the system plus apparatus is still in a superposition. Both descriptions are correct for their respective reference frames. This interpretation requires you to accept a deeply relational ontology, where properties don't exist absolutely, but only in relation to other systems. It's philosophically radical and doesn't align well with our intuitive sense that facts about the world are objective and independent of perspective. Other interpretations exist. Spontaneous collapse theories add new terms to the Schrödinger equation that cause wave functions to collapse spontaneously at random times, with collapse rate increasing for larger systems. This explains why macroscopic objects don't exhibit superpositions without invoking measurement as a special process. These theories make predictions slightly different from standard quantum mechanics and are testable in principle, though no deviations have been observed. Quantum Bayesianism, or cubism, treats quantum states as representing an agent's subjective degrees of belief about measurement outcomes rather than objective features of reality. Measurement updates beliefs in light of new information. This is philosophically appealing to some, but leaves many physicists wondering what the physical world actually consists of if quantum states are merely subjective. Consistent histories approaches try to assign probabilities to sequences of events, histories, in a way that avoids the measurement problem by treating time more symmetrically and avoiding commitment to a single definite history. None of these interpretations changes the experimental predictions of quantum mechanics for phenomena we can currently test. They all reproduce the standard mathematical formalism. They differ in their metaphysical commitments, their assumptions about what exists, and their explanations for why experiments yield the results they do. This is philosophically unusual. In most of physics, experiments eventually distinguish between competing theories. But for quantum interpretations, the empirical equivalence seems more robust. We've been doing increasingly sophisticated tests for a century, and all confirm standard quantum predictions without favoring any particular interpretation. This has led some physicists to dismiss interpretation questions as meaningless, shut up and calculate, as the saying goes. If interpretations make no empirical difference, why care which one is true? But this position is unsatisfying. Science aims to understand the world, not just predict measurement outcomes. Interpretation questions are questions about what the world is like, and these seem worth answering even if current experiments can't distinguish the options. For entanglement specifically, different interpretations give different accounts of what's happening. Copenhagen says entangled particles don't have individual states until measured, and measurement collapses the joint wave function. Many World says entanglement creates branching, with different outcomes realized in different branches. Pilot wave theory says particles have definite positions all along, coordinated by a non-local guiding wave. Relational interpretation says each particle has a state only relative to other systems, and correlations are established through interactions. These are not just different words for the same thing, they're different pictures of reality, with different commitments about what exists and how it behaves. The fact that they all make the same predictions tells you something important. The mathematical formalism of quantum mechanics is consistent with multiple ontologies. The experiments tell you about correlations and probabilities, not directly about underlying reality. Bell's theorem constrains interpretations by ruling out local hidden variables, but it doesn't uniquely determine which interpretation is correct. You can have non-local realism like pilot wave theory, non-realism like Copenhagen, branching like many worlds, or relationalism like Ravelli's interpretation. All are consistent with Bell inequality violations. Future. Experiments might distinguish interpretations if they probe regimes where the interpretations make subtly different predictions. Spontaneous collapse theories predict deviations from standard quantum mechanics for large superpositions. Some versions of pilot wave theory might make testable predictions about quantum gravity or cosmology. But for now, the choice between mainstream interpretations is largely a matter of philosophical preference. What entanglement forces you to confront is that the universe at its foundation doesn't match our classical intuitions. Particles don't have completely independent existences. Correlations can be stronger than classical physics allows. Something about locality or realism or both has to give. How you resolve this tension determines which interpretation you find most compelling. But the tension itself is experimentally established and interpretation independent. The experimental study of entanglement hasn't stopped with verifying Bell's theorem. Researchers are pushing into new regimes, testing quantum mechanics at larger scales, exploring connections between entanglement and other areas of physics, and investigating whether quantum behavior extends into domains we haven't yet probed. One frontier is creating entanglement with increasingly massive objects. The experiments we've discussed mostly involve photons, which are massless, or individual atoms and ions, which have masses around 10 to the negative 26 kilograms. Recent work has extended entanglement to much larger systems. In 2022, researchers at the University of Vienna demonstrated quantum interference with molecules containing up to 2,000 atoms. These molecules, called porphyrins and phthalocyanines, have masses up to 25,000 atomic mass units. The molecules were launched through a double slit-like setup and showed interference patterns, direct evidence of quantum superposition. This doesn't demonstrate entanglement directly. That would require creating correlations between two such massive objects. But it shows that quantum behavior persists at scales previously unexplored. The molecules are about 10 nanometers across, visible under electron microscopes. They're approaching the regime where you might naively expect quantum mechanics to break down, yet it continues to hold. Other experiments have entangled the motion of macroscopic objects. In 2021, a group at NIST entangled two vibrating drumheads made of aluminum nitride, each about 20 micrometers across and visible to the naked eye. The drumheads contained trillions of atoms moving in coordinated quantum states. By using superconducting circuits to control the drumhead's motion and cooling the system to millikelvin temperatures, the researchers created entanglement between the mechanical vibrations of the two drums. The entanglement lasted only milliseconds before decoherence destroyed it. But the demonstration proved that quantum effects aren't limited to microscopic systems isolated from the macroscopic world. You can create entanglement between objects large enough to see, though maintaining it remains extremely difficult. These experiments are probing the boundaries between quantum and classical behavior. Nobody seriously expects quantum mechanics to break down at some mass or size scale. There's no theoretical reason to expect this. But testing it experimentally is worthwhile. If quantum mechanics did fail, it would be one of the most important discoveries in physics. Another research direction involves entanglement and gravity. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes particles and fields as wave functions and operators. These two theories are famously incompatible in certain regimes, particularly at the Planck scale, where both quantum effects and gravitational effects become strong. But even at accessible scales, there are interesting questions about how gravity and quantum mechanics interact. Does gravity affect entanglement? Can gravitational fields be in quantum superposition? Does entanglement contribute to space-time geometry? Some theoretical work suggests deep connections. The holographic principle, emerging from string theory and black hole thermodynamics, suggests that the information content of a region of space is encoded on its boundary, with entanglement playing a key role in building up the bulk spacetime geometry. In the ADS-CFT correspondence, a quantum field theory on the boundary is dual to a gravitational theory in the bulk. An entanglement entropy in the boundary theory corresponds to geometric quantities in the bulk. These ideas are highly theoretical and far from experimental verification, but they suggest that entanglement might be fundamental to the structure of spacetime itself, not just a property of quantum fields living in spacetime. Experimentally testing quantum aspects of gravity is extraordinarily difficult. Gravitational interactions are weak, and isolating quantum gravitational effects from other quantum effects requires extreme precision. But there are proposals. One idea is to create a superposition of a mass in two different locations and measure whether the gravitational field is also in superposition. If you could detect gravitational effects from both locations simultaneously, that would demonstrate quantum superposition of the gravitational field. This requires exquisite sensitivity, measuring gravitational fields from milligram masses separated by millimeters, but might be possible with advanced optomechanical techniques. Another proposal involves entangling two masses through their mutual gravitational interaction. If gravity can mediate entanglement, this would prove that gravity is quantum mechanical at some level. The experiment would place two masses in spatial superpositions and look for entanglement that could only arise from gravitational interaction. Several groups are working toward this, though success is likely years away. There's also research into entanglement in exotic systems. Physicists have created entangled states in Bose-Einstein condensates, where thousands of atoms share a single quantum state. They've entangled photons across wavelengths spanning the visible to infrared spectrum. They've created time-bin entanglement, where particles are entangled in when they were created rather than in spatial or polarization degrees of freedom. High-dimensional entanglement is another active area. Instead of qubits with two possible states, you can work with qudits, quantum systems with many states. Photons can carry orbital angular momentum, quantized in integer multiples of a fundamental unit. By entangling photons in orbital angular momentum with many possible values, you create high-dimensional entanglement that can encode more information per particle and offers certain security advantages in quantum communication. Researchers have demonstrated entanglement in orbital angular momentum spaces with dimensions exceeding 100. The technical challenges are significant. You need to control and measure high-dimensional states precisely, but the applications in quantum communication and computation are promising. Another frontier is entanglement in condensed matter systems. Superconductors and superfluids involve macroscopic numbers of particles in entangled quantum states. Topological phases of matter, like fractional quantum Hall states, have exotic entanglement structures that might be useful for robust quantum information processing. Recent experiments have probed entanglement in these systems by measuring entanglement entropy, how much entanglement exists between one region of a material and another. This is technically demanding because you can't directly measure entropy. You have to infer it from measurements of correlations, and use theoretical frameworks to extract the entanglement content. Results confirm theoretical predictions in many cases. Entanglement entropy in gapped phases grows as the boundary area between regions, not their volumes. In gapless phases, it has logarithmic corrections related to the number of gapless modes. Topological phases have additional constant contributions related to topological invariance. These patterns connect entanglement to fundamental properties of quantum phases of matter. There's also work on multipartite entanglement, entanglement among more than two parties. GHZ states and W states are two distinct types of three-particle entanglement with different properties. GHZ states have all three particles maximally entangled together, while W states are more robust to loss of one particle. Understanding multipartite entanglement structures is important for quantum networks, where many nodes might need to share. Entanglement. Researchers have created multipartite entangled states involving dozens of photons, ions, or superconducting qubits. These states are useful for quantum metrology, making precise measurements, because entanglement can enhance sensitivity beyond what's possible with independent particles. The standard quantum limit for measurement precision scales as 1 over the square root of n for n particles. With maximally entangled states, you can reach the Heisenberg limit, scaling as 1 over n, a quadratic improvement. Quantum metrology applications include atomic clocks, gravitational wave detectors, and magnetic field sensors. Entanglement-enhanced measurements are starting to move from demonstrations to practical implementations where the enhanced sensitivity matters. Another research direction is dynamical aspects of entanglement. How does entanglement spread through a system after a local perturbation? This is relevant for understanding thermalization in quantum systems, quantum chaos, and the scrambling of quantum information. Experiments in systems of trapped ions and cold atoms have tracked how initially localized entanglement spreads through a chain of particles. The spreading typically occurs at a characteristic velocity related to the interaction strength between particles. Understanding this dynamics helps in designing quantum algorithms and understanding fundamental limits on information propagation. There's also interest in measurement-induced phase transitions. Recent theoretical work suggests that systems undergoing both unitary evolution and measurements can exhibit phase transitions where the entanglement structure changes qualitatively depending on the measurement rate. Too few measurements and entanglement grows, creating volume law entanglement entropy. Too many measurements and entanglement is suppressed, creating area law entanglement. The transition between these regimes is being explored experimentally in systems of trapped ions and superconducting qubits. Long-distance entanglement distribution continues to advance. China's quantum satellite Micius has extended entanglement distribution to thousands of kilometers. Plans are underway for global quantum communication networks using constellations of satellites. The European Quantum Communication Infrastructure Initiative aims to build a quantum communication network spanning Europe. These aren't just scientific demonstrations. They're infrastructure projects aimed at practical, secure communication. The technology is maturing from laboratory experiments to engineered systems with specifications, reliability requirements, and commercial viability considerations. Research is also probing the limits of entanglement. How much entanglement can you create? How long can you store it? How efficiently can you convert it between different physical systems? These questions have both fundamental and practical importance. One surprising result is that entanglement is monogamous. If two particles are maximally entangled with each other, neither can be entangled with a third particle. Entanglement is a limited resource that must be shared. This has implications for quantum networks, where distributing entanglement among many parties requires careful protocols to allocate this resource efficiently. Throughout all this research, the goal is twofold: understanding nature more deeply and harnessing quantum phenomena for technology. Entanglement sits at the intersection. It's one of the most distinctively quantum features, impossible to explain classically, and it's essential for quantum information applications. The next decades will likely see entanglement move from a foundational puzzle to a practical tool. We're already seeing this transition in quantum key distribution. Quantum computing and quantum sensing are following. As the technology matures, entanglement will become something engineers work with routinely, not just a topic of foundational debate. But the foundational questions won't disappear. We still don't fully understand what entanglement tells us about the nature of reality, how it fits with relativity and gravity, or whether the universe at its deepest level is built from entanglement in ways we haven't yet grasped. The research continues on both fronts, building better quantum technologies and probing deeper into the conceptual foundations. And the two efforts inform each other in ways that make this one of the most vibrant areas in contemporary physics.